Hey everyone, we're back. Previously, we looked at the fundamental theorem of algebra and Descartes' rule of signs, and looked into how both of those tell us the existence of zeros in the polynomial. So we were only determining the number of zeros that exist and their type. So just recapping on this, the fundamental theorem of algebra told us only the number of complex zeros. Whereas Descartes' rule of sign added to that and said, okay, so we know how many zeros exist. This tells us then, of those zeros, how many could be positive, negative, or imaginary. But again, we don't know from this where these zeros are located. So today we're going to be looking at a test that could help us get a better idea of where some of the zeros are, and then from a couple of tests we'll be able to hopefully factor a polynomial and find every zero. Okay? So something to think about. When we use Descartes' rule of sign, it told us, we have so many combinations of positive, negative, and imaginary roots. We talked previously that a complex number is either a real or imaginary. So imaginary roots we're going to save for another day, but real roots, we can even separate that further into rational and irrational. Remembering, rational, this could be any number that can be written as a fraction. So -3/2, 5, -1, 0, 5/3, 27 tenths. Any number that can be written as a fraction, we consider it to be rational. And the exact opposite for irrational. If it's a number that cannot be written as a fraction, we call it irrational. So square root of 2, pi, square root of 7, this number e, and so on. So these are actually, we can have these as zeros. As odd that would be, we could have these. But our test today that we're focusing on brings light to these types. So this is our focus for this lesson. Okay. So, of the complex zeros, of the imaginary, we're focusing solely today on our positive and negative, and solely on those that are rational. And I want to say at this moment, there is a test. This test is the rational root test. And what it says is any polynomial, given any polynomial, any rational root, remember this is a root that can be written as a fraction, any rational root must have the following form. And I believe we've seen this before in Algebra 2, so we're seeing it again here. So we see that any root that is rational is a fraction where our numerator is a factor of the constant term divided by the factor, a factor of the leading coefficient. And again, possibilities have positive, negative. So this is what every rational root of a function must be made up of. So I'm giving you an example here. So I took 6x squared minus 11x minus 10. I factored it. You could check me here if you wanted to. You could pause the video and check my work. But we get factors of 3x plus 2 and 2x minus 5. And from that we get zeros of -2/3 and 5/2. So if you look carefully, what we're saying is any polynomial, the rational roots the numerators are factors of the constant. So you think our constant's 10, is 2 and 5 a factor of 10? I would think so. Again, remember, when I say factor, I'm saying that these are two numbers that can divide into 10, or 10 can be divided by them. So then our denominator, factors of the leading coefficient. So here's 6. So we see 2 and 3, and I would again think that 2 and 3 are in fact factors of 6. So this is just one example how our numerators must be factors of the constant, and our denominators must be factors of the leading coefficient. Just so we're not writing factor of constant, factor of leading coefficient every single time, we're gonna utilize P for factors of the constant and Q for factors of the leading coefficient. This is just what our textbook uses, I believe. I think we could have used any letter, but just P and Q is what we're going to be using here. So let's test this out with this knowledge, this understanding. Let's write a list of possible zeros. So let's say we have, first of all, let's make this our goal. Find all possible factors, or possible zeros. Okay. So notice I added the word here, possible. It's important to say that because the lists that we are getting, I'm in no way saying that these are all roots of the polynomial. These are just possible roots, and we have other steps that we can take to narrow this list down. But let's say our function is 5x cubed minus 2x squared plus 4. 5x cubed minus 2x squared plus 4. So this test pays no attention to our middle terms, just the leading and constant. So the possible rational roots are, that's P over Q, P, positive, negative P over Q. P, these are all of the numbers that can be divided into 4, or 4 can be divided by. So that would be positive negative 1, positive negative 2, and positive negative 4. And then our denominator will be all of the possible factors of the leading coefficient. So it's positive negative 1 and positive negative 5, and that's it. And with this, we're going to break this out, and we're going to expand this into a list of rational numbers. So how we do this? I take my first factor in the numerator and divide it by each in the denominator. So I would have so 1 divided by 1 remains 1. 1 divided by 5. Okay? And then move on to the next. 2 divided by 1. And then 2 divided by 5. 4 divided by 1. 4 divided by 5. And that's it. So we can look here, 1, 2, 3, 4, 5, 6. We have, that makes 12. We have 12 possible roots. Rational roots. That's I mean, considering we have a degree 3, which means that we only have 3 complex zeros, which means that not necessarily all 3 are rational, we have 12 to choose from. If there is a rational root, it must be on this list, and that's important to say. Any rational root of f of x must come from this list. Just an important thing to note. Let's try another. So say we have g of x. Okay, so let's make this a little more interesting. 6x to the power of 7 minus 5x to the power of 5 plus 2x cubed plus x minus 8. What I find interesting with this test, I guess you call it a test, is it does not matter what's going on inside of here, which I find incredible because I could have nothing here and our possible roots are still the same numbers because it only depends on the first and last. So our possible rational roots. Again, that's positive, negative, p over q. Okay, so factors of 8. So numbers I can divide 8 by. Positive, negative 1, positive, negative 2, positive, negative 4, positive, negative 8. Factors of our leading coefficient. So numbers that I can divide 6 by. Positive, negative 1, positive, negative 2, positive, negative 3, positive, negative 6. Okay. Easy enough. So we look at each numerator number placed with a number in the denominator. Let's work this out. Let's make a rather large list, so we'll put little brackets here to group it all together. So 1 over 1 is still 1. 1 over 2. 1 divided by 3. 1 divided by 6. Then we move on to the next step. 2 divided by 1. 2 divided by 2 is 1 again. So we are going to get repeats here. We are going to get repeats. We just wouldn't write it twice. So 2 divided by 2 we already have. 2 divided by 3. 2 divided by 6, which is 1/3, we already have. Move on to the next number, 4. 4 divided by 1. 4 divided by 2, which is 2, we already have it. 4 divided by 3. And 4 divided by 6, which is 2/3, we already have. Move on to the next. 8 divided by 1. 8 divided by 2, which is 4, we already have it. 8 divided by 3. And 8 divided by 6, which is 4/3, we already have it. So this is the end of our list. So let's just take a moment here right now to think about exactly what we're seeing. So a degree of 7, 7 complex zeros, not all of them have to be rational. We have a possible 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So double that, 20. I'm doubling because of the positive negatives. 20 possible rational roots to test. Okay, and we could easily just go through and check every single number. We could go through, we've learned that a root, when placed into the function, will equal 0. So I could place 20 numbers into our function and look for which ones equal 0. That is a valid method. That could be a little time consuming. Some of you are probably thinking, well, couldn't we just place the function into the graphing calculator and look at the graph? No, we cannot just look at the graph of this, because that defeats the purpose of doing this whole process. The process is here, looking at the math, the computation that leads us to that. So it is a lazy, I will call it a lazy approach to just using the graph. We will need to look at other methods of finding the actual zeros. Okay? So let's look at a situation where we have a polynomial and we look for how many zeros there exist, what type of zeros exist, the possible rational, and how we narrow that list down. Because we have 20 here, how do we narrow that 20 down to something more manageable? Okay? So let's do that using this function. Let's use this function f of x equals 2x cubed plus 3x squared minus 8x plus 3. Okay? And what we're doing here again is we are finding all zeros of f of x and writing f of x as a product of factors. And essentially, we're going to try to write this in factored form. Okay? Are you ready? Let's go. We begin by using our fundamental theorem of algebra. Fundamental theorem of algebra. So by this, we can say degree 3 tells us that there exists 3 complex zeros. Where are they? We don't know yet. We just know that there's 3. Okay, next. By Descartes' rule of sign. It tells us exactly the types of functions. So this is where we have positive zeros, negative zeros, and imaginary zeros. So we have to look at our f of x and f of negative x. Okay, f of x, just copying this down, 2x cubed plus 3x squared minus 8x plus 3. We're looking for sign changes. If you recall Descartes' rule of sign, we look for sign changes. So positive, positive, no. Positive, negative, yes. Negative, positive, yes. So that was 2 sign changes, which means we can subtract an even number, or just subtract 2 to get 0. Right now we know we have either 2 positive zeros or no positive zeros. So looking at f of negative x. So in the previous video, any odd exponent, our sign changes. Any even exponent, the sign stays the same. So we would have positive 2 would become negative 2x cubed. Our 3 remains positive. 8 would become positive. And our constant always stays the same. So in this, sign changes. Let's see. Negative, positive, yes. Positive, positive, no. Positive, positive, no. It's only one sign change. So let's look at this situation. If we have, knowing that we have 3 total, if I have 2 positive and 1 negative, we would have no imaginary. If I have 0 positive and 1 negative, I must have 2 imaginary. So I'll just drop this one down. Okay? If you saw in the previous video, or if you looked at the notes, our imaginary zeros will always come in pairs. Meaning we're always going to have 0, 2, 4, and so on. Why exactly does that happen? We'll examine more in the next couple of lessons. But for now, just know we should always be increasing by 2 for our imaginary roots. So what do we have going on right now? We have a function that has a degree 3. We know that we have different combinations of positive, negative, imaginary roots. So from this point, this would be where we now use our rational root test. So where we find positive, negative, P over Q. These are the possible locations. These are the possible rational roots. So P are the factors of the constant. So We have a constant of 3, so our factors are 1 and 3. So then we have q, factors of the coefficient, or sorry, of the leading coefficient. That would be positive -1, positive -2. Not bad, and this is a rather small list relative to the previous one where we had 20 possibilities. So we say our group is 1 over 1, 1 over 2, 3 over 1, and 3 over 2. Not bad. I mean, we have eight possible roots to test, knowing that eventually we're going to get down to at least 2 positive, 1 negative, or at least 1 negative. So that's some kind of important to think about. But where do you begin? Could you just take each of these, plug them into your function, and hope you get 0 the first time? Yes, you could, but here's a suggestion I'll have for you. Because 1 will always be a possible root for most of these problems, actually, we ask ourselves, is positive 1 a 0 of f of x? So in other words, we're asking, is x minus 1 a factor? Okay, so there are 2 ways of doing this. I can either look to see f of 1 and see if it's equal to 0, or I could use synthetic division and place my coefficients at 2, 3, -8, and 3. Go through that and hope that I get 0 here. Okay, so both are valid ways of doing this. The reason why we're choosing 0 is this. Over here, if I plug 1 into my function, 2 times 1 cubed plus 3 times 1 squared minus 8 times 1 plus 3. So we get, I'm going to simplify this. This is just 2. This is just 3. This is just -8. This is just 3. I want to kind of share this with you. Maybe you're seeing this already. When I plug 1 in, when I place 1 into my function, I get the coefficients. So we want to get 0 from this. So if I combine these right now, 2 plus 3 is 5, minus 8 is -3, plus 3 is 0. Okay, I could have, and we can in the future, when we are checking if 1's a 0, we can look at the coefficients of our functions, add our coefficients together, and see if we get 0 when we add them. That is essentially what we were doing right here. So I would say 2 plus 3 minus 8 plus 3, and we would see if we get 0. If you do, then 1 is a 0. Okay? So we plug, so we know it's a 0, so we know we're going to get 0 over here, so let's go through synthetic division. Okay, so drop the 2, 2. 1 and 2, 2. 3 and 2 is 5, 5, -3, Hold on 1 second. Oh yeah, -3. -3, 3 and -3 is 0. Okay, so we already knew we were going to get 0. So what we have is x minus 1 is a factor. We are left with 2x, again, we had a cubic function, so this is quadratic. 2x squared plus 5x minus 3. And if I want to factor it again, I could now choose another number off of our list and plug it in and place it into this and hope I get 0. But any quadratic function, this is quadratic. Any quadratic function, we can use our factoring methods, we can use the quadratic formula. And since we want factors, it's going to be better for us to actually factor it and not use the formula in this case. So when we factor this problem, you can check my work, but we should get 2x minus 1 and x plus 3. So our zeros are x equals positive 1, x equals positive 1/2, x equals negative 3. So let's compare this to Descartes' rule of sign and our finding there. So we have two positive rational roots, which meant that we had to have one negative root, and we do. Okay? So there, we are going to look at this more, look at this process more when one is placed into it and it doesn't exactly work. I encourage you to replay this video, watch this video again, and go through this. I have another example in the notes that you can look at, because we, in a situation when 1 isn't a factor, we just keep picking numbers. We just keep picking numbers and look and hope that we get 0 as a remainder. And we just keep factoring. Our goal is we keep using synthetic division until we get a quadratic. Because once I get a quadratic term, then we can factor it using other means. But I encourage you, look at the notes that I've posted with this video, post your comments, your questions in the classroom, and when we come into class, we will practice this skill. So today we went from knowing exactly how many zeros exist, knowing their types, positive, negative, imaginary, to adding to that the possible rational roots that we have. And one way, one approach of how we can narrow this list down. And that approach is using 1, adding the coefficients for 0, and going from there. Okay? So until our next video, post questions like I said again, and we'll talk later. Bye.